Hello! In this video we're going to look at solving literal equations, and I'll explain a bit what this is about and then we'll get right into examples. This is for learning intention number 47. Solve literal equations. So literal, we know what solving equations is. So literal means it means in terms of letters. So if you had the equation ax equals b and wanted to solve for x, what you'll do is you'll divide both sides by a to get x equals b on a. And that would be your answer. And that's a literal equation because it's not x equals 2. It doesn't have a numerical answer. It's got an answer in terms of letters. An important thing with literal equations is to state the domain restriction as well. State the domain restriction for the variable. These are the two key points. It's in terms of letters. Make sure you state the domain restriction if there is one. And you'll see what that means with these examples. So let's jump right in with example 1. Solve for q given that 2 log base 3 of p plus 5q equals 4. So this is where our strong algebra skills are needed. We need to be very confident with our log laws, with our algebra in general. So it's like peeling an orange. You start from the outside. We're solving for q. You start with the thing furthest away, which is this 2 out here. Let's divide both sides by 2. So you get log base 3 p plus 5q equals 2. Now I'm going to use some log laws. So if you need to look up your log laws to find out what I'm about to do, please do so. What you can do is you can put a 3 down here on both sides. So you can take each of these to be a power. So I've just made it 3 to the power of log base 3 of p plus 5q equals 3 squared. The beauty of that is this actually cancels this. So the 3 log base 3 goes away. And you get p plus 5q equals 9. So that's one way to handle it. One way to think about it. Another way is to just rewrite it like this. So it's like that to the power of that gives you that. So 3 squared equals that. Same thing. Now we need to solve for q. How are we going to solve for q? Well, we're going to subtract p from both sides. So we get 9 minus p. And finally, we're going to divide both sides by 5. So we get 9 minus p on 5. Okay, so we've made our solution as a literal equation, but I said state the domain restriction. So what do I mean by that? Well, I mean here, if there was a certain value q couldn't take, then we'd have to be very conscious of that. But this looks fine to me. It looks like there's no divide by zeros, there's no square roots, there's nothing like that. So that looks okay. We don't have to worry about a domain restriction there. So that's our final answer for example 1. Example 2 looks like a doozy. Prove that all of this equals 0. Well, this is going to take index laws, log laws, the whole shebang. So let's look at example 2. Okay, well, if we add 2 logarithms with the same base, we can multiply what's inside there. So that's the same as saying log base 10 of x squared y to the 4 on y cubed z squared z cubed x. And we've still got this minus log base 10 of y to the z cubed x to the 4 minus log base 10 z squared x to the 5 on z to the 4. Okay. Now what we can do here, this minus here, means we can divide the contents of our two logarithms because they're the same base once again. And it's the same story here. So you can divide and then you can divide. You work from left to right. So it becomes log base 10 x squared y to the power of 4, and we're going to divide by this stuff here. So we've still got our y cubed, well that's z to the 5 x. We're going to divide by the stuff here, so we're going to put that down the bottom like that, and we're going to put that down the bottom as well because that's a minus, so that's divide. Okay, this is starting to get a little messy. What are we going to do now? Well, let's multiply out this section. So we'll get log base 10 of x squared y to the power of 4, big vinculum, got y cubed times y, which is y to the 4, z to the 5 times z squared, which is z to the 7, x times x to the 5, which is x to the 6, over z cubed times z to the 4, which is z to the 7, whoops, and x to the 4. Okay, we need some extra room. This is a big problem. Alright, so we know from our fraction tricks that that's going to pop up the top. So we get log base 10 of z to the 7 x to the 4 x squared y to the 4 over y to the 4 z to the 7 x to the 6, which equals log base 10 x to the 6, x to the 4 times x to the 2 gives us x to the 6, y to the 4 z to the 7 over, and it's the same thing down the bottom, x to the 6, y to the 4, z to the 7. That all cancels to give 1. And 10 to the power of 0 equals 1. So that equals 0. We've proved it. That's our answer. Let's have a look at example 3. So I encourage you to have a go at that example 2 yourself. And see if you can do it now that you've viewed the solution. See if you can apply the log laws correctly to get the answer. Alright, example 3. If y equals m plus e to the power of bx, solve for x. We have a literal equation. We need to solve for x. Well, let's minus m from both sides. Whoops. Let's start again. Alright, I'm going to delete that. Let's try again. We're up to example 3. This time it won't run off the screen. We have y equals m plus r e to the bx. Okay, so we minus m from both sides. It's peeling an orange. Work from the outside. Divide both sides by r. Now we rearrange this based on our logarithm laws. And then we divide by b. Okay, that's all well and good. We've solved for x there. And you can see it's 1 on b, natural log of y minus m on r. That's our answer. So I haven't chosen any ones that require domain restrictions, but it's the sort of thing where you get, say, root x, and you have to say that x has to be greater than or equal to 0. That's that sort of thing, where you have to state the domain restriction. So I hope that helped with literal equations, and if you have been, thanks for watching.